All right. Finally, we get to 5.4 logs, and we begin. So, what is a log? Well, let's take a look at this hypothetical situation. We know that if we go 2 to the power of something, we can get 8, right? And x would be 3. Perfect. Well, what about if you had something that didn't work out so nicely? So what about 2 to some power equals 9? How would you figure out what x equals? Obviously, it's going to be a little bit more than 3, right? 2 to the 3 is 8. We've been looking at this stuff graphically, so we've been graphing, say, this power function, this exponential function that looks like this. There we go. Right? And then we can graph y equals 9. And where those two things intersect gives us the answer. In this case, it'd be 3.169925. I went and calculated it. Okay, so that's one way to solve the problem is graphically, but that's not very convenient all the time. So basically, logs answer this question here. How many of one number do we multiply to get another number? So in other words, if you want to get 8, you go 2 times 2 times 2. So you multiply 3 2's to get that answer. So another way of writing that statement is like this. Log base 2 of 8 equals 3. So what does that mean? Well, logs are a way of rewriting exponential questions where the exponent becomes the answer. In other words, the log is an exponent. So you take this statement, 2 to the power of 3 equals 8. You can rewrite it as a log and you say, okay, the base becomes the base of the log. The answer is called the argument, and the exponent is the answer right there. Okay? So, the exponent becomes the answer. The base of the power becomes the base of the log. The answer here is called the argument, and that is the log rule. Now, I got this fancy little thing off the internet. It's a little color-coded, but it shows you where everything goes. Okay, so let's do some practice on just taking equations like this or statements like this and turning them into logarithmic form. So let's see, writing this one, 5 squared is 25, great. So I go log, the base becomes the base of the log. The exponent is the answer and the 25 becomes the argument. So we'd say log and base 5 of 25 is 2. This one here, log, so the base of that becomes the base of the log. The answer to that becomes the answer to the log, and then that's the argument. Boom. Another one, oh, what if we have some negative exponents? That's what this is talking about. So, well, this is the base. So we can say this is log base 2. Okay, the exponent is the answer, and then this is the argument. There we go. Now you can write it like that. You can also put some little brackets around the argument. Just gonna slowly throw in like notation stuff like that. So here's a very similar one. So this is gonna be log. 6 is the base. Okay, this is the argument. So we can write it in brackets if we like. Equals the exponent. That's the answer. There we go. Let's take this one. So log, the base is 81. The exponent becomes the answer, so the answer is a half, and then what it equals to is now the argument. So again, you can use brackets there if you like. This one here, log base 8 equals the exponent, and there's the argument 2. This one here, log base 4. Now let's see, the argument or the exponent is the answer, so negative a half, and then that 1/2 goes in there as the argument. And last one, log. So here's the base, so there's the base of the log. The exponent is the answer, and the argument is there. Wonderful. Doing great. Now, what if we go the other way? We have a log, and we want to put it into exponential form. So now we're going backwards. So the base of the log is the base of the power. The answer to the log is the exponent, and then that is the argument like that. Now you should get something that makes sense. Like these ones you can double check. Like 3 to the power of 3 is 27. Okay? All right. This one here. So base is 2. The answer is the exponent, and then the argument is the old answer. answer. So 2 to the 5 is 32. This one right here. There's the base, 2, exponent, -3 equals argument. And indeed, 2 to the -3, we do the reciprocal, it's 1/8. Perfect. Perfect. This one here, 36. Now, the answer is the exponent, so 36 to the 1/2 equals 6. Remember, fractional exponent, so this is actually the square root of 36 equals 6, which makes sense. Either way is fine. Now, this one here, base is 7. The answer is the exponent, and the argument is the old answer. So 7 to the 0 is 1. Perfect. Great, we're doing great. All right. Now, changing from exponential to log form and back is an important skill. You'll be doing it a lot more. So let's do a couple more. Although at this point, you should be getting like, okay, I get it, but that's good. A couple more. So this one here, let's see if you remember. Log, the base of this is the base of the log. The exponent becomes the answer, and that becomes the argument. Perfect. This one right here, log, so the base is 3. The exponent becomes the answer, so -4, and then the argument is the old answer there. Perfect. Last one. Base is 7, so log, base 7. The exponent becomes the answer, the argument is the old answer. So there we go. Backwards again, doing these ones, so going from log to exponential form. So this is the base, so 3. The answer is the exponent, so 3 to the 4 equals the argument, 81. Makes sense. Old base, 5, so 5 to the 3 equals old argument, 125. 6 is the base, 0 is the exponent, and 1 is the argument, so 6 to 0 is 1. Doing good. All right, now we get to what does a log graph look like? We knew this day was coming. So what does a log graph look like? Well. Let's compare. So the graph of y equal 2 to the x to the graph of y equals log in base 2 of x. Somehow I'm telling you these two things are related. So let's see. There's a reason we started with these exponential graphs. So let's do y equals 2 to the x first. Now, so let's just pick a couple easy points, like maybe -2, -1, 0, 1, and 2. So here we know we're going to get a quarter, a half, 1, 2, 4. Right? And you should know that general shape, so the y-intercept is here. When x is 1, we get a half, and that ought to be good. We'll sketch the other one there. And then when x is 1, we get 2. And when x is 2, we get 4. So there's our exponential graph. All right. Now, how are we going to deal with the log graph? Well, we know how to rewrite this, right? So let's rewrite the log graph. So if we take this, then this would be the base. Oops. So this would be the base. 2 raised to the power of the answer, so it'd be 2 to the y equals the argument. What just happened there? So here's the log graph written in exponential form. X and y traded places. So it used to be y equals 2 to the power of x. And now it's 2 to the y equals x. We know what this is called. This is called an inverse, right? When y and x trade places. So what's my prediction for the log graph? Well, my prediction for the log graph is that I'm going to be taking my xy points on the original function, and they are all going to become yx because it's an inverse. Let's see if that's the case. So if we plug in some numbers here, like for example, if I start with my y values, I'm going to have to go backwards, right? So if I plug in the y value of 1, what am I going to get? So if I plug in, let me do it this way. Let's go -1, 0, 1, 2, whatever. Okay, so let's start with y value of 1. Plug in y equals 1. 2 to the 1 is 2. Now, Do we have the point 1, 2 on the other side? Ah, we do right here. So the point 1, 2 becomes 2, 1. Well, what if y was 0? Anything to the power of 0 is 1. Do we have the reverse point over here? Aha, yes we do. We got the point 0, 1. So it seems like this is becoming an inverse. If I use -1 for y, then I get a half for x. Do we have that point somewhere? Oh, there it is. This is really looking like an inverse. If y is 2, then x would have had to have been 4. Right there, okay? So it's an inverse. Perfect. Let's sketch it. So the point 1, 0 becomes, the point 0, 1 becomes 1, 0. The point 1 for x, 2 for y becomes 2 for x, 1 for y. What other point do we have here? We could do, we didn't get any negative ones for x, but that's fine. So we'll use this one here. This one was -1/2. So when x is 1/2, y is -1. Perfect. All right. Interesting fact. We didn't talk about the asymptote just yet. So the original graph has an asymptote at y equals 0, right? That's the graph of y equal to the x. So when we do the inverse, my horizontal asymptotes like that become vertical asymptotes. So the logarithmic graph actually has an asymptote right here at x equal 0. Now we'll actually see that in a question why that is, but if you just do the inverse, that's what you would get. Is x equals 0 vertical asymptote, and there's the graph of y equals log base 2 of x. Okay? Now that is a lot of stuff to digest. That is huge. So at the bottom of the page here, I have a conclusion. Okay, so a log expression is the inverse of the equivalent exponential expression. So for example, if you have y equal 5 to the power of x, if you do the inverse, you get this, which is the same thing if you turn this into logarithmic form. If you take this, turn it into log form, it's log in base 5. The exponent becomes the answer, and there you go. Perfect. What is it? Let me see. Let's. Maybe it's not this one, it's this one. It's log base 5. The exponent becomes the answer, and that becomes the argument. There you go. So that is that. Beautiful. Okay? So, at the end of the day, they are inverses. Okay? So, logs, just to write again, are inverses of the corresponding exponential function. That's what it is. Boom! Okay? Inverses reflect over the line y equal x, which is why I drew that line there. And boy, that is a lot to digest. That's a lot. All right. Whew, I think we need a break now. Let's take a quick break. So let's talk about your calculator a little bit. So now we know how to take an exponential expression, turn it into a log. We know how to take a log and turn it into an exponential expression. We know that a log is just the inverse of the corresponding exponential expression. So now we can kind of graph them. What about your calculator? How do you use your calculator for logs? Well, your calculator, unless you have one of the really fancy ones, will always just do logs in base 10. So that means you'll be going log base 10 like that, okay? That's called the common log. Our number system is base 10. So our number system goes 0 to 9, right? There's 10 numbers in there. Just like how square roots, so if I go to the square root of 6, like we don't write the index, right? We don't ever bother writing the 2. It's generally understood that it's there. Your calculator will just probably say log. So it's generally understood that unless there's something written here, it's base 10, okay? So let's take a look at a quick question. So if I write log of 100 equals 2, it's generally understood that because there's nothing there, it's base 10. So we could take this, we could say, okay, well the base becomes the base here, the answer is the exponent, and the argument is the answer in the exponential form. So 10 to the power of 2 is 100. Well, what's the value of this one? Okay, well let's try. There's nothing written there, so it's base 10. So it's 10 to the power of something has to equal the argument. So what's the something? Well, 1, 2, 3, 4. So it's 10 to the 4. So if you were to type in on your calculator log 10,000, the answer the calculator would give you would be 4. How does it get it? It's thinking about this equation. It's saying 10 to what power equals 10,000. What about this one? So let's write it. 10 to some power has to equal 1 over 100. Well, this is going to be a negative exponent, and the answer would be negative 2. So if you type this in on your calculator, it would just say negative 2. Beautiful. Let's do a bit more practice with that. Let's evaluate these ones. Okay? So our strategy for evaluating is change to exponential form. Now on your exam, you may have to evaluate some logs without your calculator. So you have to do it like this. You could say, okay, I'm evaluating this one. So the base has to equal something, right? So 2 to the power of x equals the argument. And then you can use what we learned the other day when you have these exponential equations. How do we solve this? Like you can either think and be like, oh, well, you know, the answer is what? What is it, 6? I believe it's 6. Or you would have to rewrite it. You know, 64 is 2 to the power of 6. So x is 6. Now be very careful. If you were to do the work like this on the exam, I've actually introduced a new variable without defining it. I'd be losing half a mark if I just said x equals 6. Okay? So on the exam, just to be really clear, when you're stating your answer for this, you'd show your work. You'd show your work like this. But at the end of it, don't circle that, just go equals 6. Or rewrite log base 2 of 64 equals 6. Okay? Otherwise, you have to say, like, let x be the answer, or something like that. So you have to define your variable, okay? They're really picky about stuff like that. It's kind of weird, but I get it. They're setting you up for math, like, if you go into university level math, sort of. All right, this one. So 4 to some power, right? We don't know what it equals, but 4 to some power equals 64. Well, you might be able to just guess this one and say, oh, well, the question mark has to be, is it 3? It's 3. Okay, so you would just write that. So here's your work. You'd have it off to the side, and then you would just write 3. That's your answer. Here's another one. Let's do it the proper way. So the way I expect you to do it on the exam, you go 3 to some power equals 81. I might have to rewrite that one. 81 is 3 to the 4. Okay, the answer is 4. Boom. Don't believe me? Type it, or you won't be able to type it in on your calculator. My bad. Okay, solve for x in the following questions. Here we go. So if they give you the question like this, then you're allowed, there's already a variable x there, so you can say 7 to the power of x equals 7. So x has to equal, that's a 1. X equals 1. This one here, 7 to the power of 0 equals x. What's x then? 7 to the 0 is 1, so x is 1. Wonderful. This is sort of like an important, there's a couple things here actually, the reason I'm doing these particular questions. So a couple facts you need to have in the back of your mind. So if you didn't notice, when the base and the argument match, the answer is almost going to be 1. Okay, so if I said, hey, you got log base 12 of 12 equals x, right away you're like, oh, base and argument match, x is 1. Otherwise, you got to do all that work. So that's one that you need to keep in the back of your brain. The other one is, if your log equals 0, then the answer is 1 as well, because you're going to have 7 to the power of 0 equals x. Okay, so these are 2 log questions that you should know. So like, not memorize these particular, and I hate to say memorize the concept, I should really say like understand the concept, okay? So a log that has the base and the argument equaling has to equal 1, here's why. If the log, no matter what the base is, if it equals 0, the answer is going to be 1. So if I said, hey, log, base 1, 2, 3, 4 of x equals 0, right, you're going to be like, oh, x is 1, because it's the base to the power of 0. All right, let's do some more. Here we go. So now it's right here. So the base is x. That's going to be the exponent, and the argument is the old answer. So what to the power of 5 is 32? This one you just sort of have to think and be like, oh, well, 2 to the power of 5 is 32. Or if you have trouble with that, you could rewrite this. 32 is 2 to the 5. So there you go, same exponent, so the bases must match. That's another way to think of it. That's kind of a tricky one. This one here, oh, this isn't a log question. This is a question from yesterday. So yeah, that'll happen to you on the exam. They'll just throw in the middle of the log questions, you get an exponential question. So here we need to get the base. Get the bases the same. All right. So this one already has a base of 3. This one I need to convert, so it's going to be 9. Remember, the power in there is the numerator and the index is the denominator. I need to get the same base still, so 9 is 3 squared, and it's raised to the power of a quarter. So we have 3 to the x equals 2 times a quarter is 2 quarters, which is a half. But now I have the same basis, so I can say x equals 1/2. Remember, I just reduced 2 quarters. Wow, that's a hard one. This one, let's see. So this is the base, so it's x raised to the power of the answer equals the argument. So again, you could rewrite this. So if you don't already see the answer, like, oh, it's 2 to the negative 3, your only other option would be to rewrite this as something with a base of 2, right? So now the exponents match, so the bases must be the same. Done. Here's another one, base of 27. So 27 raised to the power of the answer a third has to equal the argument x. All right, well, that's just the cubic root of 27, right? And that's 3. All right, everything's coming together. It's amazing. Okay, we're getting close. I keep checking my notes because when we get to I, something really important happens here that explains the asymptote on our graph. So another one, base of x raised to the power of the answer equals the argument. Okay, so the square root of 64 equals something to the power of 3. Which one is this? G? Where'd it go? Where'd it go? Yes, well, we could try to rewrite 64 as, oh, I don't know, what is it? Is it 4 to the power of 3? I believe it is. All right, wonderful. So, what would x have to be? I'm drawing a blank on this one for some reason. Well, geez. Let's do it this way. What's the square root of 64? It's 8. There we go. It's been a long day today. So, 2 to what power is 8? Well, if you're still not sure, 8 is 2 to the power of 3. Exponents are matching. Bases must be the same. So, x is 2. Wow, that was kind of hard. All right. And then we'll skip for now. Too hard. We'll skip. Okay, this one. Woo! This one's very important. Very, very important. So I even wrote, it leads to an important conclusion, so something must be happening here. So let's try turning it into exponential form. So it's going to be 2 to some power x equals the argument. Now here we go. Is there a way to get a -4 just putting in some exponent here? And the answer is that does not exist. Right? There's no way that I'm going to raise 2 to some power and pull out a -4. Like, if you think, like, well, 2 squared is 4, how are you going to get the negative? There's no way to get that negative. Does not exist. Well, what does this mean for us? This means that arguments cannot be negative. In fact, I'll go one step further and I have to say arguments must be greater than 0. Now, why? Let's go back to the graph. Where's that graph? It's because of the graph. Our old horizontal asymptote of y equals 0, when we do the inverse, becomes a vertical asymptote x equals 0. So I can't be negative. I can't get negative x values, negative arguments, and I also can't get exactly 0. That's why. So that came from the graph. it took us until this example to realize maybe why, okay? Now this is just one example that sort of illustrates, right? You know, I'll let that marinate in your brain tanks. This is a crazy lesson. All right, well, should we do some more practice? Well, let's see. We've done so many of these now. I don't think we need more. We really don't. No. You know what? I'll give you a moment. Like, we've done so many of these already. I'll give you a moment, and then I'll write up some answers here. I don't think any of these are worth doing again in huge detail. Yeah, that's what we're gonna do. So you're gonna get 6 for this one. For this one, you're gonna get, you know, I'll do this one. So you can say let x be the answer. So if you are going to do it this way on the exam, then you could go 4 to the x equals 1 over 32. Right? And then you could say, well, you know, rewrite the base of 4, so it's 2 squared. And then there's the x. And then this is 2 to the negative, what? 5. Okay, so same base, go 2 to the x equals negative 5. You can equate the exponents, and you get x equal negative 5 over 2. Okay, if you don't do this whole let x be the answer thing, then you would just do your work off to the side, and then you would just write equals negative 5 over 2. Okay, so it's up to you how you want to do it on the exam. On this one, you're going to get 2/3. All right, so this one I will do. Sometimes, every once in a while, they throw on like, oh, can you estimate this value? So they put this on the non-calculator part, and they get you to estimate it. They might get you to explain why. So you can think of it like this. You're going to estimate it. Well, and again, we're going to be like, let x be the answer. So let x be the answer. So let's see. It's 2 to the power of something has to equal 10. Well, how would I estimate this? Well, let's see. Let's think. 2 to the power of 3 is 8, and 2 to the power of 4 is 16. Okay, so if 2 to the power of something is going to be 10, then my answer's got to be somewhere between 3 and 4. Okay, so that would be the logic. So then you'd be like, okay, so then you just guess. Be like, x is approximately 3.2. And if they ask you why, you would have to explain in words, you know, well, 2 to the power of something has to equal 10, 2 to the power of 3 is 8, 2 to the power of 4 is 16, the answer must lie between 3 and 4. Boom! Alright, that's that one. Woo. Yes, let us conclude, because that was really hard. Let's make sure that we know the difference between a log graph and the exponential graph. Okay, so let's know the difference between an exponential graph and a log graph. We did this before for 2 to the power of x. Let's do it for this one. So if I say, hey, graph y equals log base 3 of x, how are you going to do that? Well, I would start thinking about the original exponential graph, which would be 3 to the x equals y. Okay, now, that's the original one. Or, better yet, so this is the original. You could take this and write an exponential form. So if you wrote an exponential form, it'd be the base, 3, raised to the power of the answer equals the argument. And you can go ahead and graph this. You need to remember a couple of those key points, right? So either you remember that it's this graph and you're doing the inverse, right? Or you do this one and you say, okay, well, we have a vertical asymptote at x equals 0. Why? Because it's the inverse of this one, which has a horizontal asymptote at y equals 0. What else? The graph, log graphs usually go through the point 1, 0. Why? Because these graphs go through the point 0, 1. So you really need to know your exponential functions in order to draw the log ones. So what would we need on the exam to have a good sketch? Well, you're going to need that asymptote, x equals 0. if you write it in exponential form, then you can make yourself a little table of values in reverse, right? Where you can start picking like easy values for y, like -1, 0, 1. So if y is 0, 3 to the 0 is 1. There's the point 1, 0. If y is -1, you get 3 to the -1, which is a third. So when y is -1, x is a third. So you're really close to that asymptote. You'll have to label that. X is a third, y is -1. And if y is 1, then you get 3, right? 3 to the 1 is 3. So when x is 3, y is 1, right there. So you need at least 3 points, including the intercept. So the graph looks like that, and like that. So there's the graph of y equals log base 3 of x. Okay? Believe it or not, sometimes they give you log graphs that have transformations. We'll look at those some other time. They don't go too crazy though. So compare that to the original graph of y equals 3 to the x. Well, they're just inverses, right? So that would be the big takeaway. They are inverses of each other. Right? So if I have this graph, then I can just do the inverse. So my vertical asymptote becomes a horizontal asymptote. And all of these xy points I have become switched, they're yx. So when x is -1 over here, y is a third. And I'd have to label that -1 a third. And then we had this point, which was 1, 0. Well, that becomes the point 0, 1 right there. And then we have our last point that is 3 for x, 1 for y. That's going to become 1 for x, 3 for y. And we have our exponential graph. Boom! Whew! I'm not going to lie, I am tired. So, concluding remark, to wrap it all up nicely. Definition of a log. Everything we learned can be summarized by these two sentences. So the logarithmic function y equal log in base b of x, where b is greater than 0, so that's the base. The base must always be greater than 0, and b does not equal 1, is the inverse of the exponential function y equal b to the x. Perfect. We didn't even talk about domain, but the domain of this would be x greater than or equal to 0, right? We saw that the domain has to be x greater than or equal to 0 because of that asymptote, right? So domain, like that. Perfect. Okay, that was a long one. I am tired. You can do exercise 5.4 now. I will try to make some sort of summary video for logs in the future, a 10-minute math one, but bye for now.